talking about volumes using a technique called cylindrical shells. Right. So, as you've seen in previous pages, the washer method can be a little much. All right. So, what we're going to do is use a different method that can often replace the washer method, and see if that's more to our liking. All right. So, the idea here is that what we're going to essentially do is take rectangles that are parallel to the axis of revolution and spin them around the axis, and that's going to create you guessed it, cylindrical shell, or so the shell of a cylinder, as in a cylinder. But if you look at the diagram here, where the middle portion is bored out, all right, so it's only the shell that you would get. It's only a shell of itself that you would get if you were to spin that rectangle around the axis. Now, if you do that for infinitely many rectangles over the given interval, that would encompass the desired volume. All right, so I'm just going to kind of walk you through where this idea starts and leads us to, all right, because it's interesting to say the least. All right. So you get that blurb up there, but you can read through that. The gist of it is what I just explained. All right. So this process here that you see on the remaining portion of the page really just kind of gets at the idea of the cylindrical shell method. All right. So if P is defined as the distance from the axis of revolution in the center of the rectangular strip, then what is the radius of the outer cylinder? All right. So if it's going to the center of that rectangle, all right, so directly smack dab in the middle, and that rectangle has a width of W, then it's going to have a half width, if you will, of 1/2 W. All right. So, and that would be on either side of the midline. So 1/2 W added to the value of P would get you the radius of the outer cylinder. All right, so that's just going to be P plus 1/2 W. Now, what's the volume of the outer cylinder? Well, volume by definition, let me get back to black here. Back in black. So pi r squared h. All right, so we know that this is going to be our radius. And so the height is the height. It's unknown. It's an unknown, but we're using h to represent it. So the volume is going to be pi times r squared multiplied by h, where r is P plus 1/2 W. All right. So we could leave it at that, I suppose, or we could distribute it out. It's one of those things where it's kind of like maybe we see where this is going first before we distribute it out. All right. So number 3, if P is defined as the distance from the axis of revolution to the center of a rectangular strip, then what's the radius of the inner cylinder? All right. So that's going to be the same idea, but we're going backward from P 1/2 W, so P minus 1/2 W. So the volume there is essentially the same idea anyway. So the volume is going to be pi times P minus 1/2 W squared. Could have just wrote it. The amount of time it took me to do all that. All right, so what's the volume of the cylindrical shell? It would be the outer cylinder minus the inner cylinder. So it would be this minus this. Now you see that we have a common pi and a common h, so those can be factored out. So we're looking at p plus 1/2 w squared minus p minus 1/2 w squared. All right, so we could distribute, a little double distribution here. So p squared, the outers and inners will each be 1/2 pw. So add them together, you get pw plus 1/4 w squared minus p squared minus pw plus 1/4 w squared, all bracketed and contained and multiplied by pi h. All right, little distributive property, just running through the negative. All right, so reversing the signs, and it looks like a lot of nice cancellations here. And so really we got 2 pw's multiplied by pi h. So 2 pi h, really. Well, I could say 2 pi and then hpw. You know, you kind of look at what we have in the diagram and you see, well, the rectangle's width typically is a d, like dy dx, something like that. So that probably should come at the end. So I'll hold off with the w, but we'll have the p and the h, whatever order you want, and then w. All right, so that's the volume of the cylindrical shell. All right, so if you have, let's say you have some bounded region, and you want to spin it around an axis, and I'll come up with just a simple one. And over that interval, based on the diagram I drew, it actually makes more sense to revolve it around the y-axis. So let me make that adjustment real quick. I'd have a rectangle that's parallel to the axis of revolution. And so that's going to get spun around just like you saw up here. So this is what we should end up having. I mean, it's really not perfect, but it's the best I can do. All right. And so, yeah, and so what we're going to do is we're going to fill out the area or the region by repeating that process infinitely many times. And so, yeah, it's definitely a process, but this kind of ends up being the main idea behind it. Color is orange, and then copy, and then paste, and then color, and then orange, and then resize, and why it didn't oh, I didn't copy the same figure. Okay, well, anyway. Yeah, so something like this. All right, and so yeah, like I said, you just do that over and over and over again from beginning to end, or the beginning to the end of the region. So this would be over the interval of A to B. And so when we collectively put all this together, we come up with an integral over the interval of A to B of 2 pi PHW. That 2 pi is constant multiples, so 2 pi can come out of the integral. The P and the H, well, the H is going to be the height of the rectangle. The P is the distance from the rectangle, the center of the rectangle, to the axis of revolution. All right, so the short answer on those is it depends on what the axis of revolution is. The W is going to be d something. All right, because it's representing some thickness. So in this case, it's a dx, but it could be a dy if it's oriented the other way.